Well, hello there. Let's talk a little bit today about pumps and piping systems. This is video one. Gonna start with something that we call a pump curve, and this is a pump curve for a centrifugal pump. Centrifugal pump is a pump that's on a shaft. It's got what we call impeller blades. The water comes out of the center of the pump, comes in at this location, and the blades are spinning this way. We call that place where it comes in the volute, and as the water moves outward, it picks up more and more kinetic energy, to the point where when it leaves the I guess we'll get it this way. Well, when it leaves, it has picked up more energy than when it came in, and that mechanical energy of the spinning blades is converted to kinetic energy of the water. But then as that kinetic energy of the water actually up here in the volute um, slows down, the energy stays, the kinetic energy is converted to pressure energy, and the pressure entering the pressure of the water entering the pump is higher leaving the pump. So there's an increase in pressure, change in pressure. Not a great picture, decent description. Let me just talk about the energy again. From when the water comes in before the pump at a certain diameter, and then after the pump leaving at that same diameter, kinetic energy is going to be the same, but the pressure before is less than the pressure after. And we could talk more about this in a learning conversation. So the purpose of a centrifugal pump is to increase the pressure of the fluid. Well, let's see here. Got some daylight coming in. All right, so now I'm going to draw a pump curve. And in our pump curve, we have head, also represented by a differential pressure, increase in pressure, on the y-axis. And flow rate, let's go with a V dot, volume flow rate, on the x-axis. And centrifugal pumps, when you get them from the manufacturer, have been tested to give you a graph of head versus flow rate. And centrifugal pumps typically have a graph that looks about like this. What that means is that when the pump is pumping at low flow rates, it can give you a very high increase in pressure. But when the pump is pumping at high flow rates, it gives you a low increase in pressure. So there it is, pump curve. Now let's talk about a resistance curve. When water is flowing in a system, or when a fluid is flowing in a system, there's often friction. Friction causes resistance to flow, and as we learned in fluids, the way that we identify that is through something called head loss. And head loss is a decrease in pressure decrease in fluid pressure due to friction. Well, we can take a look at, that's kind of a crappy curve. We can take a look at a plot of the head loss in a system. Let's just say that our system consisted of one valve. And valves typically have pretty high head loss, especially valves whose position changes to cause flow. Globe valves are an example, but flow control valves. When you close the valve some, you get more friction. You open the valve wide open, you have less friction. Again, we'll have head, which also is a representation of decrease in pressure versus volume flow rate. The equation is that head loss is proportional to volumetric flow rate squared. You may remember Darcy's equation, and this was for head loss in a pipe. We had friction factor times length times velocity squared over 2 times diameter times gravity. Well, the important thing to note here is the velocity. Remember, volume flow rate is equal to area times velocity. So if head loss is proportional to velocity squared, then head loss would also be proportional to volume flow rate squared. You should recognize that this should give us a parabola. And in the parabola, if there's 0 volume flow rate, there'd be 0 head loss. And the more volume flow rate there is, the more head loss there is by a factor squared. So this is called a head loss curve. Now, again, on the same axis as we just recently had our pump curve. So if we start out and have a system that has one pump and one valve, and it's a closed system, and we let all of the head loss of the system sort of take place in this valve, and we got a pump curve from the manufacturer where the pump curve crosses the head loss curve. We call that the operating point. And while the pump can operate anywhere along this pump curve, and the fluid can flow anywhere along this head loss curve, notice that there's only one place for this system where the pump curve and the head loss curve intersect. And so that defines the point. It defines what the volume flow rate would be in this system and what the head would be. And by head, what we're saying is, well, that's how much pump head is required across the pump and how much head is being lost in the system. This is a representation of pump curves and system curves. So if you're taking a competency right now called Pumps and Piping Systems, We start with these two basic curves, the pump curve and the head loss curve, and recognize that where they are going to be operating is at this intersection. Where we will go in future videos is to explore what happens when you have more than one pump in a system. And lots of systems have more than one pump. And sometimes those pumps are in parallel, like this. Sometimes those pumps are in series, like that. And we'll learn how to manipulate the pump curves when either of those cases happen. And most systems have far more than one simple valve causing all of the resistance to flow. We will look at, well, what happens when there are many valves and they are in combinations of parallel and series, and how do we find the operating points. So this course focuses on those fundamentals using the concepts of energy and flow rate and head.